Hi everyone, welcome to lecture 8 of Synchrotron X-rays for micromechanical analysis. This will be the final lecture of this current course, and today we're going to be talking about processing diffraction data, fine-grained sometimes called powder, even though the samples might not necessarily be powder. Polycrystalline specimens, in the far field. The subtext being what do we do? Continuous firing. So just as an example, the previous data we were talking about in the far field, we had individual diffraction peaks. We were able to associate these diffraction peaks with crystal orientations that were present. And then in lecture 7, we talked about how we could get information like the center of mass, the orientation, and the lattice strain tensor from the individual grains or crystal orientations that were present. In a fine-grained specimen, all the diffraction peaks start to overlap, and we get continuous Debye rings on the detector. We talked about this in lecture 4 of this course. For today, as part of our analysis, we will assume that we can neglect the effects of crystal volume position, as we know, all that means is that we put the area detector far away from our specimen, and that we can neglect the effects of instrument broadening. Basically, this means we're not going to worry about how the instrument can sometimes make our diffraction peaks larger. We want to talk about the effects of material on diffraction peaks. So we have our detector, and we have some Debye rings. What we know is that each point has contributions in crystals that lie on a crystallographic fiber. Which just meant that all these orientations share one direction in the crystal coordinate system. But since we have at each point on these rings, we have lots of crystals contributing, we're going to be looking at things so we're going to be looking at crystal response in the average sense. It's important. So that leaves us with an important question of how much averaging do we actually want to do when we look at these crystal when we look at these sets of crystals. Now, for most of today, we're going to be concerned about the distribution of intensity in this radial direction. Which we can relate to twice the Bragg angle. So we're going to, for shorthand, we're going to talk about this in the 2 theta direction. So we want intensity versus 2 theta. So what we're going to have to do is we're going to have to integrate our diffraction data along this angle that we're going to call eta, or azimuthally around the ring. And I was just talking about how much we want to average. So our question is, over what angular range So our first option Option 1 is to integrate completely around the ring. So we can integrate all around the ring if we know that the state of the material does not have any angular dependence, or it does not, lattice planes do not respond differently or have different probabilities of being present as a function of the sample coordinate system. Or in other words, if the distribution of intensity is isotropic. So if we know that all crystals are responding the same, or all showing the same behavior, it makes no difference if we integrate all around the ring and look at a large number of fibers. So for example here, so if we take an integral all around the ring, there's a large subset of fibers that are contributing to all that intensity that we collect. Our second option is to integrate over a small subset, or a small angular range. We want to do this when the response or the distribution of lattice plane orientation is anisotropic. So at the crystal scale, the mechanical response is almost always anisotropic. There are very few materials that might be close to isotropic, but if we're looking at the mechanical response, something like strain as a function of angle, we're always going to want to cut up our Debye ring into small angular ranges. And in addition, most materials in their as-processed state tend to have what we call texture, or a preferred distribution of crystallographic orientations, which would mean that the intensity varies around the ring because certain lattice planes are preferentially oriented in certain directions. So we would like to, one, figure out that distribution of orientation around the ring, and two, look at how that that distribution response under mechanical load. So if we integrate over a small angular range here, we cut a small pi wedge and integrate azimuthally, there's only a few sets of a few fibers that are contributing, and so much smaller, we're looking at a much smaller subset of crystals, and we can kind of look at their response individually. Now, I've talked about integrating this distribution of intensity azimuthally, but it's worth talking about how that's actually done. And I'm going to talk about two options just to give you an idea of how it happens. And part of the problem is that most area detector data comes on a pixelated regular grid. And a regular grid of values does not lend itself particularly well to a polar integration that we're just talking about. So two simple strategies to get you thinking about the problem. So the first, so here's just a grid of pixel values. This is just like a small piece of a detector. And what you would do is you draw a bound, bound in 2 theta, so just a bounded region on a ring. And what you do is you'd grab the intensity on each pixel that falls within your angular bounds and sum those all together to azimuthally integrate. So that's a simple strategy. A more complicated strategy would be to actually take our pixelated grid and map it to a new polar grid using interpolation methods. So for each point here inside our new polar grid, we'd find where it sits on our original pixelated grid and interpolate between pixel values. Once we have our polar grid, operations like azimuthally integrating become fairly straightforward. And we can do standard numerical operations like Gaussian quadrature to perform that operation. And then when we're finished, hopefully we have a distribution of intensity versus 2 theta. And what we'll have is diffraction peaks that we can now start to analyze to look at the response of different sets of different subsets of crystals. One way to think about these distributions of intensity is that there are a sum of contributions from all of the crystal volumes which lie along the fiber. So there's lots of little peaks together that sum together to form this one peak. And what we want to do is we want to analyze this peak to figure out some information about these subsets, about these crystals underneath that are contributing in intensity. So what can a peak from our integrated wedge tell us about the contributing volumes of crystal? Here's our peak. So the first thing is that the area under the peak is proportional to the volume of crystal participating. Two, the centroid tells us what the average lattice plane spacing is in that set of crystals. And from that, we can figure out lattice strain. So we talked about the area under the curve and the centroid. And lastly, the width provides a measure of the spread of lattice plane spacings in that set of crystal. More importantly, the spread of strain. And I'm going to come back to this in a little bit. So how do people pull this information out? So usually researchers did an analytic peak function. The data and then you can find those previous values of interest. So the choice of peak can be chosen for expedience. The peak looks Gaussian. Sometimes it might be convenient to fit a Gaussian to the data. Or there could be deeper theoretical reasons for why you would choose a certain peak shape. But what's important to remember is that your choice of peak shape is another model that you've thrown into the data. So you have to be very careful when you choose a peak that you know why you're doing it. And the fact that your choice of peak functions can affect the final answer that you get out, whether it's the area under the curve or the centroid or the width. You can put in the exact same data to different peak functions to get different answers out. Some of the most common used ones are Gaussians, so intensity is equal to an amplitude times an exponential where the sigma is related to the width of the peak. This 2 theta naught is the centroid, and the amplitude is related to the height of the peak and the total area under the curve. So we can figure out those 3 pieces of information that we were wondering about earlier from this analytic function. Lorentzians are also often used. Then there's an amplitude, and then this term gamma, which is related to the width. Then we have a term related to the position of the peak, and another term related to the width. So again, amplitude related to the area under the curve. Gamma is a width term, and we can also pull out the centroid. So the last peak type that I'm going to talk about are the pseudo void peak functions, and all that is a combination of a Gaussian and a Lorentzian with the rule of mixtures, where n is the mixing parameter. Where n varies from 0 to 1. So you've picked a model, you've chosen a peak. Important question to ask is, how well does that actually represent the data? And one way of doing that that's often used is the Goodnessoffit parameter. And in the literature, R is often used. So the R value, a general R, is the sum of a weight, and we're going to sum over all our measurement points, or of our intensity measured minus our intensity fit squared these are discrete measurement points summed over the square of all our measured intensity points. So the lower the R value, the better. And this can kind of tell you generally if your choice of peak function or your choice of model is working well. This weight value can change depending on if you want to weight certain parts of the function more than others. You can often weight this so that the high intensity values are more important than the low intensity values. Say you want to catch the tips of the peaks. You want to make sure your R value, that your function is doing well there. Or if you want to catch the background, you want to make sure that this value preferentially weights towards low intensity values. So I want to come back to peak widths a little bit. I just want to touch on the subject. I could probably easily cover a whole class just talking about peak widths. So we can measure peak widths, and we can measure the spread of our peaks. What's important is to keep in mind, what do they tell us? Because there's a lot that goes into them. And what contributes? So we've got lots of crystals and lots of volumes contributing to each point and each peak. And so we can imagine that distributions of intergranular strains contributes. So even if a crystal has the exact same crystallographic orientation and they're both contributing, they might have different neighborhoods and different boundary conditions as they're loaded. And so that might cause them to have different strain states and different sets of lattice plane spacings. So they might both contribute. Intragranular strain distributions. As a crystal is loaded, it's a complex boundary value problem, and the strain and stress can vary throughout a grain. And then each of those crystal volumes, which make up our grain, will all have different sets of lattice plane spacings and also contribute to peak broadening. There's also broadening due to defects. Things like dislocations, vacancies, and interstitials. And what those will do is those will broaden what you can think of as the little individual diffraction peaks of each crystal volume. So each crystal volume, if it has defects present, will transition from that delta function, which we derived in lecture 3. If we have a perfect crystal volume, it was a delta function. And as soon as defects become present, that distribution broadens out, and that will also contribute to peak broadening. Fourth contribution is thermal fluctuations. Atoms do not sit statically in space. They do vibrate, and that the magnitude of that vibration will also change the width of diffraction peaks, because each individual atom never sits in the exact perfect lattice position that you need to create a delta function. So you get a spread of positions, which spreads out your diffracted intensity. And finally, there are also size effects, which we've also worked out. As the size of our coherent crystal volume shrinks, the diffracted intensity distribution will also broaden out, just because of those size effects and the Fourier transform of that shape function that we talked about in lecture previously. So the reason I bring all this up is I just want to make it clear that there is a lot going on in those diffraction peak widths, and that it's still an active area of research to be able to tease all this information out all at once. But it is in there. The last thing I want to talk about is, so we've analyzed our peaks, we've pulled out information about the volume that's present, maybe the average lattice plane spacing for the subset of crystals that are pointed in this, or set of lattice planes that are pointed in a certain direction, maybe the distributions of strain. How can we look at this data and get an understanding of the anisotropic response? And so what's typically used is a pole figure, and we're going to talk about mapping our data to pole figures. So a pole figure is a way of representing or plotting values associated with lattice planes aligned along different sample directions. The most common one, the one that you might be most familiar with, is an orientation pole figure. Which is the probability This is proportional to intensity. Finding lattice planes with an orbital parallel to a sample direction. And I'm going to show examples at the end, which will hopefully make this a little bit clearer. But I just want to go over the mapping process really quickly. So we have our detector, and we have our rings. We might also have multiple frames that we took as we rotated a specimen. And so along the ring and along our set of frames, we might have values of intensity, a function of 2 theta, eta, and omega, or lattice strain. Or maybe peak width. So if we remember from the lecture 6 notes, we can take those 3 angles and map them directly to reciprocal space. So each point on the detector corresponds to an outgoing wave vector, and we know that the difference of the outgoing and the incoming wave vector is the scattering vector. And most importantly, when diffraction occurs, the scattering vector is equal to a reciprocal lattice vector. And the mapping that we worked out between our angles and a point in reciprocal space in the lab frame equal to 4 pi theta for lambda cos theta cos theta and again, we can go from the lab to the sample coordinate system with the coordinate transformation, which we're now also experts in operating with. So that's how omega gets incorporated. So we now have all our intensity in reciprocal space. And if we remember, that intensity or strain, all those values of those mappings tended to fall on shells in reciprocal space. And that was lecture 4. And so we can take something like our intensity, we've mapped that to point in reciprocal space. We can now take each of those shells so from a family of lattice planes and map that to the unit sphere. So all we have to do is take the unit vector associated with our reciprocal lattice vector. And so we can take our values like intensity strain, and widths, and plot them each on a unit sphere for each family of lattice planes. And so I've talked about it. It'll be a lot easier to see with some examples. So here's examples of pole figures which were gathered from diffraction data that look just like that series of images. And then we've applied the mapping that I just discussed. So here's an example of an orientation pole figure. So each of these colors, and this has been normalized, but this is a dark region corresponds to the likelihood, or a red region corresponds to a high likelihood of finding a set of, in this example, 110 lattice planes along this sample direction plotted on the sphere. And you can see there's actually quite a bit of variation of color, which corresponds to a large variation of probability of finding lattice planes along different directions. So this is actually a heavily textured material that has a fiber texture, because you can imagine that you can rotate sets of lattice planes along a single crystallographic direction or along a fiber. What we have here is an example of a lattice strain pole figure, so of a set of lattice planes. And this material was in tension. So you see here at the top, this is red, so we have positive lattice strains along the loading direction up here, and that we actually have these blue values along these sides. This corresponds to Poisson contraction. What's important is that the lattice planes are all responding anisotropically with respect to the sample coordinate system. This is why we don't want to average out all that information by picking a large angular range of eta to integrate over. So that's it for the final lecture. I want to thank everyone for listening. Hopefully, if there's feedback or other topics that you think should have been covered or want covered, you can send me an email and maybe we can cover those in a future course. Thank you for listening.